I welcome you all for the next video lecture, and this is an 7th video lecture in computational intelligence. In this video lecture we are going to discuss about game playing, which would be in the first unit of computational intelligence. And what are the outlines we are going to see in game playing is, firstly we are going to see what is mean by games, and we are going to make a decision in games and the decision making process done by the optical decisions in games, and what are the strategies we follow to make a decision. An alpha beta pruning algorithm is an efficient way of deciding who wins and who loses the game. And also we are going to see various types of games, and the games of imperfect information, and the game that includes the various elements of chance, and why, for, and what are the games we are going to see in this slide. And basically the game is a form nothing but multi-agent environment. The games are referred in a multi-agent environment. Basically we are having two types, that is cooperative versus competitive multi-agent environment. And competitive multi-agent environment give rise to the adversarial search. That is, adversarial search is a main searching strategy we are using in the games. And why we are going for this study of the games is, and as we all know that the games gives us fun and also makes to think in an intelligent way. And here historical entertaining is a main way why we are going for these games. And we are going to make an easy way to represent an agent that is restricted to small number of actions. And we are going to see a difference or relations between the games and a search, and why we go for search and why we go for the games. And search is nothing but here the no adversary will be there, that is opponent will be there, but in games we have the adversary. And here the solution of the search is that finding the goal state is the main solution of using the search strategy. Here the solution is making effective move for every possible opponent reply. The time limit, the estimated time limit would be based on how many steps it takes and the estimation of cost from start to goal state through the given node. And here the time limit is an approximate solution. Time limit force is an approximate. And the evaluation function is, how do we evaluate the search is the estimation of cost from the start state to reach the goal state. And here it evaluates the goodness of game position. And what are the example for searching is path planning, scheduling activities. And here the example for games are chess, checkers, backgammon, and Othello. And here we are going to make a comparative between deterministic and chance, and also perfect information and imperfect information. And deterministic imperfect information comes under chess, checkers, goes, and Othello. Here the chance which comes under perfect information is backgammon, monopoly. And also the chance which comes in an imperfect information is bridge, poker, Scrabble, and nuclear war. And we are going to concentrate mostly on the deterministic type. And what are the setup we need to make while playing games, and this is the thing we are going to discuss in this slide. Basically it needs 2 players, and we are going to take that to be in max and min, and we are going to find and give reward or award to the winner, and loser gets the penalty. And what are the various search we have in this game, or initial state. Initial state is the initial stage of how we start with the games, and successor function is the move from one state to the other. And terminal test have the game achieved its destiny, that is game finished or not. And utility function is the terminal stage. Example, +1 for those who are winning and -1 for loser, and draw 0 if the game doesn't win or lose. And here it use a Max use a search tree to determine the next move. And the tic-tac-toe game, as we all know, the tic-tac game is a partial game tree for tic-tac move is given in this slide. And what would be the optimal strategies used in this tic-tac game are, we are seeing with 3 types of value, that utility value, max value, and the min value. And here the both the players, we need to check whether both the players play optimally, and we need to draw the optimal strategy by using the min max value of each node. And the min max value is based on the utility value n. The max value, we are having a min max value of S successor, and the min value is also defined by the min max value of the successor if a node is min node. And this is a example of 2-play game tree, and max would be represented by a triangle, and the min value is a reverted triangle. And this would be an example here. And each layer alternatively, the max and the min follows alternatively, and here each max node in the leaf layer has been provided with a certain values. And we are going to find what would be the value for the root node. Basically, the first min node contains 3 branches, 3, 12 and 8. Min of 3, 12 and 8 is chosen, and that value is replaced as a min node. Similarly, for the other 2 trees, the min value out of all the leaf node is chosen, and that would be given as a min node in the first layer. And similarly, and out of 3, 2 and 2, which would be 3 branches protrude out of A2, and we are going to see 3 values, 3, 2 and 2. Out of the 3 value, the maximum value 3 is chosen as a root and min max decision tree. What if min does not play optimally? If min does not play optimally, it really the maximizes the worst case for max node. And min max algorithm, and the min max algorithm is detailedly explained here. If the function is max value, what are the steps we need to follow, and if the function is min, what are the steps we need to follow. This is clearly explained in this slide. And what are the various properties we have for this min max algorithm? Basically, the time and space complexity are the 2 various terms we need to concentrate on. And optimality, B exponential m will be taken for time complexity, and B into m will be taken for the space complexity. And multiplayer games, similarly like a 2-play game tree, the multiplayer games involve the many players to be followed, more than 2 players, and single minimax value becomes the vector in this multiplayer games. And what are the problems of minimax searches? And here we do not examine every node, and so we need to follow a new algorithm, that is alpha beta pruning. In alpha beta pruning, we are not to complete the whole tree, but we are going to remove the branches based on certain condition which is followed in the alpha beta pruning. And we are going to see a detailed explanation of this alpha beta pruning. Alpha beta pruning. Alpha is meant for maximum, that is minus infinity value, and beta meant for minimum and with plus infinity value. And we are going to, from the leaf node, we are going to compare with the root node, and each root node will be replaced with either the min value or max value. That's the thing we are going to check. Here minus infinity is compared with 3, and where minus plus infinity is min. Whenever we are coming for this min, and we need to take plus infinity, wherever we are using with this max, we need to use the value of minus infinity. Here the plus infinity value is compared with 3, and which is said as a minimum will be replaced in the root node. So 3 is replaced over here. And similarly, from the min value, the max value is also been checked, and whether the max value is greater than 3 or not need to be continued, and if it is greater, it need to be replaced. And so 3 isn't replaced over here. And similarly, all other branches. Similarly, for the other branch, the 2, it is being referred compared with the min value, since because 2 is less than plus infinity, and that will be replaced here. And this way the root node is compared again. And similarly, the other branch also will be compared, and comparing all such branches, the max value will be replaced in the tree node. And alpha beta pruning algorithm is explained here, and here the input is taken, and the input will be returned the action in successor state with the value v. And also we are going to check for the maximum value, and if the maximum value is greater than minus infinity, then we need to replace the root node with the minus infinity value. This algorithm being explained here. And general alpha beta pruning, and it involves a natural planning way of pruning the tree in branches way, where it follows the certain condition for its pruning. The condition being explained here in the next slide. It doesn't affect the final result. Each subtree need to be pruned, and here the time complexity is found, that is O b to the power m bar 2. And when we find this time complexity, the storage capacity will be much more better compared to all other algorithm. And where here in alpha beta pruning, the cutting of search is used. Where we are going to cut off searches, we are going to check the condition. If the terminal test state, then return utility state. If the cutoff state is in depth, then we are going to return the evaluated value of the state. These are the two changes we are going to make in the cutting of search. And here we are going to see about evaluation is nothing but the performance rate depends on the quality, and it should be in the same way as the terminal node as an utility, and the computation may not be taken too long. For non-terminal state, the evaluation should be strongly correlated with the actual chance of winning. And the heuristic example is being done using a chessboard example. And we are going to detect possible moves in each state, and we are going to find who is the winner and the loser. Here the expected minimax value is found. The min-max value is basically depend on max value, min-max value of S if n is the max node. Similarly, summation of successor node P of S, expected min-max S if n is the chance node. And here in this slide we are explained with the position evaluation with the chance node, that is A1 is win. If A1 wins, that is left side, what are the various outcome stages, and if A2 wins, what are the various outcome stages, and we are going to find the eval value for both the linear transformation. And have discussed all the what is mean by games and min-max algorithm, and how would be the min-max algorithm would produce a better right tree than the left tree, and we are going to calculate which would be an expensive calculation out of all the algorithms. And alpha beta pruning we have seen, and also the utility of node expansion we have seen in detail, and both the suggestions require the meta reasoning. Out of all, the summary of this game playing is, the games are even though fun, but it is dangerous too, and being illustrated through an important points using AI. The perfection is unattainable. Many cases the perfection is unattainable. It's only an approximate result we can get through this, and it is a good idea to think about it. The uncertainty constrain the assignment of values to various states, and the games are to artificial intelligence as a grand prix racing to automobile design.